Okay, looks like I am live. So, great, let's get started. Today we're going to be talking about a couple methods of distilling models. And in essence, we're interested in first compressing our models. So can we get much smaller models that perform similarly or slightly worse than much larger pre-trained models like those that we've seen so far. Um, and so before we start, it might be good to think about why we might want to do this. And the main reason is that we care about the latency of our models at inference time. So if I have, some BERT-based QA task and I want to deploy that as a service to customers. If I'm using, say, BERT large, this is a 24-layer transformer, right? So it might, take a significant amount of time to even return the answer to a single query. And now if I have, thousands or tens of thousands of users potentially querying it simultaneously, I'm going to need a lot of compute to be able to efficiently serve this model without ruining the user experience, right? So one way in which I can speed up these models at test time is to make them smaller, right? We know that as we reduce, say, the number of layers in the transformer, we're getting rid of a lot of computations that could be causing a slowdown at test time. Also, it makes us more memory efficient. We can potentially use a larger batch size if we're batch serving our queries at test time. So there's a number of benefits that are speed and memory related associated with making your models smaller. But of course, our models are large because we get better performance when we make them large, right? We know that, for example, BERT base compared to BERT large, there's a pretty large performance gap. Oh, it looks like my thing is no longer streaming. Am I connected to the internet? Oh, okay. Okay, I do seem to be connected to the internet. Could you type in the chat if you can hear me all right? I think I was not streaming for a large amount of time there. Okay, so it says it should be back right now. All right, I'm just going to proceed. I think it's now working. Hopefully that doesn't happen again. All right, so right, let's so basically we want to make our models smaller but still have them retain the same performance of larger models. All right, so before we jump into it, we did get quite a few people requesting topics on both Piazza and also the anonymous forum. One of those topics seemed quite important for just to make sure that you properly understand the transformer. It might be good to also see it in code, or at least a simplified version of it in code, next to the equations and architecture diagrams that we've already covered. So we're going to do that on Wednesday, and we'll see how far I can get through a collab notebook. And also your homework 1, the due date is coming up in, I don't know, like 9-ish days. For that, we've made a couple of small modifications. There was a bug in one of the final problem, which we've fixed. So you should be able to. Oh, looks like it's buffering again. Okay, yeah, I don't know what's going on with my internet connection today. Anyway, we fixed a couple bugs in the last problem of homework 1, and yeah, I think it should be going pretty smoothly. All right, so Our method of making our models smaller is called knowledge distillation. So this was proposed many years ago originally, but has recently become very popular as our models are quickly growing, out of hand in terms of size for serving them efficiently. So in knowledge distillation, we assume that at training time, we've already trained or we have access to some huge model, which we'll call the teacher. And we're going to start with this teacher model, and we're going to use it to train a much smaller model called the student model. And the student is going to be trained to mimic the predictions of the teacher model. It's kind of different than just taking a tiny model and training it from scratch on, you could pre-train it if you're trying to mimic BERT. You could take, like a 3-layer transformer and pre-train it using the masked language modeling objective on 3 billion words. Or you could take the standard BERT 12-layer transformer and somehow use that to guide the training of your 3-layer transformer. And the second approach works a lot better than training your tiny model just from scratch. And so we'll go over how this process works. It was originally proposed and shown to work on vision tasks, but is now also obviously important for NLP. And again, I don't think we need to go over this at this point. We've seen a bunch of these models, but this is just a figure from a recent paper called Distilbert, which is one of many efforts to make BERT smaller but preserve its performance. This plot is basically showing the number of parameters of a couple different models that have been proposed in the last 2 years. So you see Elmo is over here, also the earliest model on this chart at around 94 million parameters. We got to GPT-1, BERT large, then we had GPT-2, which was 1 billion parameters, 1.5 billion. We had a bunch of models, Roberta, etc. GPT-3 is like off the chart. It has way more parameters than anything else we've seen. But the method proposed in this paper, Distilbert, it has only 66 million parameters. So it's definitely smaller than something like BERT. Okay, so let's go through this process of knowledge distillation. It's actually very, very simple, and we've already learned all of the components of this process in previous classes, so it should be very straightforward to understand. Let's assume we have our teacher model. So we'll call it BERT. I guess this is the BERT large pre-trained model. Has 24 layers, right? So we like the performance of this model, but we don't like that it's so big and it's so slow at test time. So we know that BERT works by this masked language model objective, right? So I give it some input with a mask token. Bob went to the mask to get a buzz cut. And the model is going to produce a probability distribution over the words, over the words that could fill in this mask token, right? So maybe barbershop and barber and salon and stylist are all with some probability, and other words that are not important or not relevant to this context get a low probability here. So for every mask token, we can get a predicted probability distribution like this over our entire vocabulary using our teacher model, right? So we just assume that we have this teacher model. And so we're going to call the predicted distribution of our teacher model soft targets. So note that if I'm training my teacher model, I use the cross entropy loss computed against the ground truth word that fills in this mask token, right? So maybe in our training data, we observed Bob went to the barber shop to get a buzz cut. So now my ground truth probability distribution is this one hot vector, right? It's putting 100% of the probability mass on barbershop and 0% of the probability mass everywhere else, right? In contrast, we can view the predicted distribution produced by our teacher model as another kind of ground truth distribution for training a student model. So now if I have a student model, instead of predicting barbershop with 100% probability, I'm instead going to predict this entire distribution that comes out of the teacher model. So I want my model to produce 54% probability of barbershop, 20% probability of barber, 6% probability of salon, and so on, right? So this is very different than a one hot target where all of those components of the loss drop away except for the negative log probability of the correct word. So in this example, barbershop. In this case, every single word in your vocabulary is contributing some amount to your loss, right? So I want my model to predict that stylist has a 4% probability. And we'll go through a little later why this method of training with soft targets is potentially more informative than just training our student model with hard targets. So we've got these soft targets, which are just the predicted probability distributions over these masked words. And now we're going to train a student model. So in Distilbert, this is a 6-layer transformer. So smaller, of course, than our teacher model. And we're going to give it the same training data. So Bob went to the mask to get a buzz cut. But here, the student model, instead of predicting 100% probability on barbershop, it's going to predict this entire distribution, all these soft targets. And the loss function is exactly the same as what we were doing when we had the hard target, right? Just the 100% probability on barbershop. It's the same equation for the cross entropy loss that we've seen, but note that now the T sub I comes from these soft targets, and T sub I is no longer 0 for all of the other non-barbershop elements in the vocabulary. So I get, if I'm at the word for barber, this would be 0.2 log, and then the prediction of the student model for the predicted probability for barber. So this is the general process of knowledge distillation. We're using the predicted distribution of the teacher to train our student model instead of just relying on the hard targets. Now, in Distilbert and in many other cases of knowledge distillation, you train with a combination of soft targets as well as hard targets. So this model is also going to get a separate component of its loss, also using the cross entropy loss, with just the 100% of the probability focused on the correct word barbershop. But you're going to do a weighted average of the hard target loss with this loss over the soft targets, which are produced by the teacher model. Okay, so that is the general principle of knowledge distillation. We have a couple of questions here. So what are the measures for stating or classifying a model as small or large? That's a good question. Going back to this plot, when Elmo was released, it was considered a pretty large model in its own right. So it really depends on kind of the hardware limitations of the current time period. Something like BERT large was considered huge when it was released, but is now just like a normal model that everyone is able to fine tune on, just Colab GPUs, for example. Something like GPT-3 obviously is completely infeasible to fine tune on one or a few GPUs. So that is considered large. But yeah, it's just a function of the kind of hardware, the advances in GPUs and what can and can't fit or be fine-tuned with a reasonable number of consumer-grade GPUs. Okay, so other questions. Are soft targets produced after training is complete for the teacher model? Yeah, so you assume that you've pre-trained this teacher model, and it's, of course, pre-trained using the standard masked language modeling objective, and it's you treat it as fixed. So it's just, its sole purpose in the distillation process is to produce probability distributions of these masked tokens. And those are then used as the ground truth for the student model. Can you please explain the difference between, this is your standard pre-trained BERT. It's trained only using hard targets. And what I mean by that is if this sentence in the training data was Bob went to the barbershop to get a buzz cut, and barbershop got masked out to create this training example, then when we predict the masked word here, our cross entropy loss, our ground truth distribution is going to consider barbershop with 100% probability and a 0% probability to all of the other words in the vocabulary, right? That's the one hot distribution that we're doing at pre-training time. So we call this a hard target in that only one word is correct and all of the other words have 0 probability. The difference between a hard and soft target is when we use a soft target to train, we're actually using distribution, the predicted distribution over the entire vocabulary as training, not just this one hot distribution where all of the probability mass is concentrated on a single word. So here, like if we use the teacher's predicted distribution over this mask token as soft targets, then we have a predicted probability for every single word in the vocabulary. So we're going to force the student model to predict not just that barbershop should have a high probability, but also that these other words like barber and salon and stylist should also have probabilities that are higher than other words that don't make sense at all within this context. So that's the general intuition here. You can think of it as soft targets have the probability mass distributed across all of the items in the vocabulary, and hard targets just have them concentrated on the single correct word. Hopefully that cleared it up. If we have the hardware to run the large model, why not just use that? So there are many considerations, right? If you have the hardware to run the large model, but maybe you don't have the hardware to scale it up to, like 1,000 or 10,000 queries at coming in at the same time, right? Then maybe you benefit from having a smaller model that you can scale to the actual practical use case that you have. I mean, this is a very important problem in industry. I personally I'm working with some companies who are very interested in using distillation to make their models more efficient, so that if you have them in something like a customer-facing chatbot or some kind of API, you're not going to need to use as much compute to serve these models to your target audience. And another response to that question is, you might have the hardware to, run the model with some reasonable latency with a batch size of 1, but maybe it breaks down once you have a larger batch size, right? And there are all other types of kind of parameters that you need to vary depending on your practical use case. And in general, like if you have a smaller model, you're going to have, at the end of the day, making things faster is always going to be good for, like decreasing the costs that are associated with serving this model. So this distillation is sort of like function approximation. Yeah, so you're trying to approximate the predictions of the teacher model, right? So in a way, we're saying that capturing a soft target distribution is in some sense simpler. No, not really. So what we are saying, though, is that the soft targets are more informative than the single hard target, right? So if you look at the top 4 words in this simple example here, you see that they're all related to, barber, haircut type of things. And if I just have a hard target, I have 100% of my mass focused on barbershop. I miss out on all these like synonymous words that are also reasonable things to put into this context. So the soft target is not simpler to predict, but it does contain more information than just the simple one hot target, which is the intuitive reason why doing this training with soft targets is better than just training your small model from scratch on the hard target. Okay, so for training the student, we run a forward pass through the teacher, then use the soft targets to train the student network. This happens for every data point in our training test, in our training, I guess that means set. Yes, so you can make this more efficient, right? Because if you're training your student model, you may not want to run a forward pass through the teacher model at every batch. So instead, what you could do is do a single pre-processing step, essentially, where you run all of your training data through the teacher model and cache the predicted distributions, and then use those to train your student model. So there's no actual forward pass of the teacher model during the training process. But yeah, I mean, if it's fine, if you don't care about training time, a simpler solution might be to just not do any caching and do a forward pass through the teacher model to get the soft targets. But in principle, you're right, that's what's happening. Do we reuse the fine-tuning data set that we use for the teacher for training the student? Yeah, so that's a good question. There are many different points at which this distillation can be done, right? So what I've shown here is distilling this masked language modeling objective. So this is the pre-training step. There's no downstream task used here. So the expectation would be you take the Distilbert model, Distilbert, and then you're going to fine-tune it on the downstream training data set, as you normally would. But you could also add a distillation step at the fine-tuning phase where you make the model predict the same probability distribution over the downstream task that you would that the teacher model does, like a fine-tuned teacher model. There are many variants of this. You can check out the papers that were assigned for reading for more details, but they give a good empirical comparison of all of these different points at which you could add distillation. All right, even though soft targets are more informative, are we expecting our small model with lower capability or capacity to be able to be trained equivalently to a larger model? Yeah, so this is a good point. No, we don't expect it to be perfectly able to predict these probability distributions, but that's not our goal here. So in essence, if you're going into distillation with the goal of getting a smaller model, you're always going to be tolerant of some level of performance loss. You're just hoping to keep that the difference in performance from the student and teacher model as small as possible, and having it predict these more informative soft targets is a better way of like preserving as much information of the teacher model as we can. Okay. So just to kind of reinforce some of this stuff that I've already mentioned in answers to your questions, these soft targets are more informative than just the correct word or the hard target that we train our teacher model on. And as an intuitive reason, right, let's consider two words from this example that weren't shown, right, that are probably low probability given this context, right? So one word could be church and the other word could be and. So if we look at filling in this mask token with those two words, we have Bob went to the church to get a buzz cut. It's kind of low probable, but at least it makes sense, and it's like grammatical, and a church is a location that Bob could feasibly go to. There could be some world in which some church was giving out buzz cuts for whatever reason. But if you compare that to Bob went to the and to get a buzz cut, that's not grammatical at all, right? So even though both of these words will have a very low probability from the teacher model, we would expect church to have a higher probability than and, right? So even though there's very little probability assigned to these, the relative order of these words and the relative difference in probability is very meaningful, right? It tells us that and is much, much less likely to fill in this mask than church. So we get all of these kinds of comparisons, even with low probability words in the soft targets that we aren't getting from the hard targets. So for example, this distinction, church and it's telling the student model that this mask is likely to be a noun. It's also likely to be a location. It's not likely to be a function word. So all of this kind of information we get just from a single predicted distribution, which we don't get from the hard target. What kind of trade-off between the performance and the size of the smaller model in comparison to the bigger model do we expect? Are there any tasks where we would prefer using the smaller model? That's a good segue to the next slide. So these are the results from Distilbert. They say that in general, it retains 97% of BERT performance on downstream tasks. So you can see here they have a table. These are all of the tasks in the GLUE benchmark, which is a kind of standard classification benchmark for NLP. We've seen some of these tasks before, like MNLI is the entailment task, SST is a sentiment analysis task. So we see here BERT base, which is a 12-layer transformer. It's it's of course better than this small Distilbert model across the board, but the differences aren't that large. And in some cases, Distilbert is actually better, although these data sets are very, very small, so I don't expect these differences to be significant at all. You can see that some tasks there are huge gaps, and on other tasks like sentiment analysis, the Distilbert does just as well. But you might be wondering at this point, how well do I do if I just take the Distilbert architecture? So again, that's the 6-layer transformer. It's 1/2 the size of BERT base. And what happens if I just train a 6-layer transformer from scratch, like just a BERT model, and then evaluate it, fine-tune it for all these downstream tasks? So, before I do that, I wanted to mention that there are other works that try and distill other components of the model, not just the final predicted probability. So these, I think, are quite interesting approaches. This paper that I've referenced here introduces this model called TinyBERT, where in addition to doing the distillation over the vocabulary, they do distillation on the hidden states and the attention matrices at each layer of the transformer. So very interesting. It's basically saying we want the hidden states of our small model to be kind of predictive of, or be similar to the hidden states that you observe from the teacher model. We want the attention heads to be looking at the same places in the teacher model that they do in the student model. So you can get pretty in depth with how much you're going to apply distillation and what components of the model you're going to apply it to. So this TinyBERT does a lot more distillation than the Distilbert model does. And these loss functions, of course, the hidden state one can't really be a classification loss, right? It's a regression loss. So you can use like the square loss, which we went over when we were introducing backprop, as to kind of make the teacher hidden state and the student hidden state as close to each other as possible. Okay, so now I want to get back to the thing I was talking about before, which was what happens if you just train the student model from scratch instead of doing distillation. So there's this paper, which is called Well-Read Students Learn Better, which compared a bunch of different variants of distillation to this training from scratch method. So if you see on the slide, this bottom line here, the dashed dotted line with the X's, this is a model where you just train BERT from scratch with a much smaller architecture. So they tried a bunch of different architectures, tiny, mini, small, medium, base. You can see the number of layers and the hidden states here. The hidden dimensionality here. And these 3 other lines, the orange, blue, and green line, represent different types of distillation. And the red line, the red dotted line at the top, is the teacher model. So this is kind of the upper bound. You can see that all of these different variants of distillation are significantly, in most cases, outperforming the training from scratch method. And in some cases, this difference is really large, right? So if you look at sentiment analysis, our teacher model is like about 94% accuracy. Our train from scratch model isn't really improving even if we make it bigger. and it's also stuck around like 82% accuracy. So that's a pretty huge difference, right? Meanwhile, we see these distillation models, they actually improve as you make the model bigger and bigger, the student model, and they're coming closer and closer to the teacher's performance, and in some cases even outperforming the teacher. So, all right, we have a question here. When hidden states are compared, considering the number of hidden states are different. Oh, I guess you mean the dimensions model. So in this case, you're assuming that the hidden size is the same for both teacher and student, and you're just cutting down the number of layers, essentially. So, but like the attention, head, size, everything is the same. You're just compressing the model by reducing the number of layers. So you can say, you know, I'm going to remove every other layer, and then I can have each layer predict like the one of the layers from the teacher model. I'm not sure exactly what procedure that they followed to align the teacher and student models in this paper, but you should check it out if you're interested. But yeah, if you're going to do this kind of hidden state similarity distillation, you're going to need to have some kind of alignment here. All right, so one thing that's interesting from this paper is how, like, what exactly is the method used to get this green curve? Because this is the, okay, I guess I missed when it was buffering, unfortunately. Hopefully it's better now. Sorry about this. I can't really control my internet being bad. Right, so what is this green curve here? So in this paper, Well-Read Students Learn Better, they proposed this method called pre-trained distillation, which is supposed to be better than the method that we showed with Distilbert. So essentially, you start with a small student model, and you train it from scratch using the hard targets with on your pre-training data set. So let's say I have a BERT teacher model that was trained on Wikipedia using the masked language modeling objective. This is going to be my teacher model. Now I'm going to take a much smaller BERT architecture, say like a 3-layer transformer. I'm going to pre-train it using hard targets on the same exact training data set. So let's say Wikipedia. So that's this first gray box here. I've now pre-trained my small model. Now, in the next step, I'm just going to do distillation. So I'm going to take the parameters of my small model, and I'm just going to basically fine-tune it using the distillation objective, using the soft targets from the teacher. So I'm starting with a small model that's already been pre-trained, and now I'm fine-tuning it to make its predicted distributions look more like the large teacher models. So you can see the arrow here from the large teacher into this distillation step. Then finally, now this is my final pre-trained model, and now I can just fine-tune this on labeled data if I want to use it on a downstream task. And this is the process that is reflected by this green curve and outperforms, you know, kind of doing both of these distillation and pre-training steps at the same time, or just doing distillation from scratch without doing this pre-training step. So if you're interested in this, you should check out this paper if you're interested in using these techniques. But it's a very simple method to maximize the effectiveness of your distillation. And as you can see from these graphs, it has quite a significant improvement over the more naive methods of distillation. So is layer 1 compared to layer 1? I don't actually know, so I assume you're talking about this tiny BERT setup. I'm not actually sure how they aligned the layers of the teacher and student, so you'd have to go check out this paper for more details, but I assume they have some method of doing this alignment. What is the intuition behind pre-training? Well, of course, we know that pre-training is you know, basically the thing that makes NLP work these days. And it is, yeah, I guess pre-training to convergence using hard targets results in the small model having a good initial set of parameters, right? As opposed to just randomly initializing them and then doing the distillation from scratch. So yeah, I think probably the gap here is because pre-training gives you a much better starting point for the distillation. What about the case that the student is better than the teacher? I honestly don't know what to say about that. I don't know how you can really explain that. It might be some random effect. In general, you should not expect a smaller model to be better than a larger one. Although I will note that at least for this case, the size of the model is the same as the size of the teacher model. But yeah, even in this medium case, there's a slight increase in performance. I honestly can't explain that. I'm not sure why that's happening. What is the unlabeled transfer data in distillation? Right. I imagine this is the difference between the soft targets and the hard targets. So here, when we have unlabeled language modeling data, this is just the hard targets, and unlabeled transfer data is referring to the soft targets that you're getting from the teacher model. Okay, so that is the process of distillation and its many variants. You can, of course, explore just doing things at the output layer using the predicted probability over the vocabulary. You can also think about distilling different components of the model. There's a lot more work to be done here. I wanted to briefly switch over to another very interesting recent development in the machine learning community, which is the lottery ticket hypothesis, which is kind of another approach to obtain a smaller model that doesn't rely on distillation. So this paper was published last year. It's called the lottery ticket hypothesis, and it states that a randomly initialized dense neural network contains a subnetwork that is initialized such that when trained in isolation, it can match the test accuracy of the original network after training for at most the same number of iterations. So what this is saying is that there is some, if you take like some huge network, there's some subset of the parameters of this network that are responsible or can reach the same performance as that full huge network if you remove all of the other parameters and just train this new subnetwork from scratch. So the process by which they devised to find the subnetwork is, first you take your huge network and you randomly initialize it as you normally would. Now you train this network for some number of iterations, maybe until convergence. So you can imagine doing this for BERT, right? So I randomly initialize my BERT architecture. I train it on the masked language modeling objective for some number of epochs, and I get some final set of parameters. We're going to call it theta sub j. So now, once I have my big BERT model, I'm just going to prune away some percentage of its parameters, which essentially creates a mask, like a binary mask, 0 or 1 for each parameter in the model. Is it pruned or is it preserved? And in this paper, they use a very simple strategy of pruning weights after the model has been trained. They just, for every layer in the model, remove some percentage of the weights that had the lowest magnitude. So this is, a very simple heuristic that seems to work. There are probably other ways in which you could do this pruning, but they just chose the simple magnitude-based method to do it. So I'm going to prune for every layer like 20% or 40 or 60% of the parameters that had the lowest magnitudes in that layer. Now, the very interesting finding here is that now I have some number of parameters that have not been pruned in this way, right? The parameters that had the highest magnitudes. So now I'm going to reset those parameters to their original random initialization, and I'm going to train this network from scratch without any contribution from the pruned parameters. So those are going to be masked out of this new network. And this is called the winning ticket because even though I've removed P percentage of the parameters of this model, I end up reaching very close to the the original model's performance. So this is, at least for me, was quite unintuitive, and it just shows the importance of the random initialization. Right? There's some subset of parameters that their initialization is somehow contributing to, making the optimization easier, maybe, or making them play a more important role than other parameters. And you can detect these parameters by just pruning from a pre-trained model. So there's this paper that was assigned on the website, Lottery Tickets for BERT Network, that explores this hypothesis using the BERT model. So I just took their result table just to show the results of applying this pruning strategy to BERT base. So these are all of the glue tasks again. And here they're showing different sparsity values on each of these data sets. So 70% means that they've pruned 70% of the parameters of this model. For something like squad, they were only able to prune, say, 40% of the parameters, versus for this QQP data set, they could prune 90%. So you can see the performance of the BERT base model here is reported in this row, and the performance of their approach, which is just taking this mask and multiplying it with the random initialization and then retraining that model from the original initialization, they are able to almost exactly match the performance of the BERT base model, in some cases with quite a high amount of sparsity. So this is super interesting. And just to evaluate, they also try taking a random mask. So instead of selecting a mask that corresponded to removing the weights that had the lowest magnitudes, you could also just randomly mask out P% the parameters. And you can see that these randomly masked networks performed really poorly on the downstream task. So this indicates that this heuristic of selecting the weights that have the highest magnitudes is actually quite important. And there is, these results do show that there is a lottery ticket, the metaphor at least holds here. So yeah, this is perhaps another route that you can go if you're interested in making your models faster. Okay, so some more comments. I can imagine that pruning can be done based on the task at hand so you could definitely use some gradient-based method to figure out which parameters are maybe contributing the most to the loss function or a particular prediction. They didn't do that. I think they tried in this paper some other methods of pruning, but this method seems to be quite effective. It would be interesting to try other methods, though, I agree. By pruning, do we mean just removing the parameter from the model altogether, or just set them to 0 and no training happens to them? I mean, I'm not actually sure what the implementation looks like. I imagine it's the latter, where they those parameters, as you can see here, they're you're just multiplying this binary mask to the parameters. So I imagine that those parameters are just set to 0. But like, if you are really interested in a more efficient implementation, you would just remove them altogether. So yeah, I think those two things are equivalent, or actually maybe they're not equivalent, but you probably get some sparsity, some speed ups during training just by making your computations sparse. But I'll have to look into exactly what the implementations of this do. It's a good question. Okay. Oh, wow. It's been 45 minutes. All right. So maybe I'll try and go a little faster over this next part. I've lost connection again. All right. Hopefully it comes back soon. Okay. So it seems like it's recovered. Sorry again about the buffering. So All right, is it? Okay, it just hasn't recovered. Okay, finally back, I think. Sorry about that. Okay, so right, as I was saying, so there is an interesting connection between the process of distillation and a couple security vulnerabilities in these models. And so let's assume that you're a company, let's say you're Google, for example, and you're serving a model like Google Translate, say. So your customers who are using this model, they don't have access to the predicted probability distributions that your model is producing, right? They don't have access to these full probability distributions. Google Translate will just give you the actual words that correspond to your translation. So even if you don't have access to the full distribution, you just have access to the, say, argmax prediction of the teacher model. It turns out that you can still, using a process similar to distillation, extract a model that performs very similarly to the teacher model. So this is a case of an attack against one of these pre-trained language models. It's called a model extraction attack. And so instead of calling it a teacher model, we'll call it a victim model. It's a model that an attacker wants to steal. Maybe, I mean, you could come up with all sorts of reasons why someone might want to steal Google Translate, right? If you steal a Google Translate model, then you don't have to pay Google for using it to, translate your own data, right? So there are many advantages that you as a malicious attacker or as a competitive company can apply these kinds of attacks to models that are publicly served behind APIs. Okay, so this is, I just wanted to maybe wrap up quickly by describing some work that one of our TAs, actually, Kalpesh, did on this using a process similar to distillation. But I've also linked a paper on the website showing how the same process can be applied to stealing Google Translate successfully. But we'll just go over some simpler data sets here. Okay, so again, this is called a model extraction attack, and I'm just going to outline the basic framework by which we perform these attacks. So we have a victim model in our distillation terminology. This would be called the teacher model, which is being served by some black box API. So what that means is I, as a customer, am able to put in some text, and it sends it over to the server. The prediction happens on the server side, and then it sends back its predicted argmax prediction on the input. So if I had a sentiment analysis model, I would have something like, this is a great movie, which I feed into this API, and it gives me positive. It may not even give me the probability associated with this prediction, right? It might just tell me that the sentence is positive, not that it's like 78% positive or something like that. So this is the only information that I, as an attacker who's trying to steal this model, have access to. Okay, so right, this model is released as an API, so I can submit as many questions to essentially form a training data set for my own stolen model. So that's generally how this process works. You can view the stolen model as the kind of analog of the student in the distillation process. So here, for my queries, I'm in our work, we experimented with like the most naive strategy possible, which is just randomly sample words and concatenate them together to form inputs that you can send over to these models. So for the sentiment analysis model, I generate this query 17.3 period miles Vegas, right? It's ungrammatical. It makes no sense. But this black box model is going to spit out some prediction, positive or negative, even if the input doesn't make sense. So maybe it predicts positive on the sentence, and for this one, circle Ford had support wife rulers broken Jan family, it predicts negative. So I can submit as many of these queries as I want using whatever process I want to generate these inputs that I send over to the model. And I'm collecting for each query the corresponding label. So in the end, I get the set of like gibberish sentences paired with what the victim model predicted for each of these gibberish sentences. So now I'm basically just going to kind of replicate the distillation process, but using hard targets instead of soft targets. So I'm going to take my pre-trained BERT model, and I'm going to fine-tune it on the gibberish data set that I've collected by doing this process of querying the victim model. So I'm fine-tuning my BERT to be able to, given 17.3 miles Vegas, predict positive. This seems like a meaningless task to a human, but it turns out that even though you use these gibberish queries to fine-tune your stolen model, it actually turns out to work pretty well on real English data, which is kind of crazy. So now I have my fine-tuned stolen model, which we call the extracted model, and it actually is able to make legitimate predictions despite not even seeing a legitimate instance of the sentiment task at the fine-tuning during the fine-tuning process. So this extracted model can predict, given this is a great movie, that this sentence has positive sentiment. So of course this is a huge problem, right? Because as an attacker, I didn't even have to think about anything to accomplish this process. I submitted completely random inputs. I didn't have to use any strategy to cleverly construct inputs designed to reveal the most information about this victim model. I didn't care at all about that. I just submitted random gibberish, got back some predictions, and if this model is able to work well, then this is a very, very low cost attack, right? So we did these attacks on estimated their costs using Google's. They have an NLP API that serves a bunch of these models, and it's actually quite cheap. So if you wanted to use Google's NLP API, it's about $1 for 1,000 inputs or 1,000 API calls. So if you wanted to extract a sentiment analysis model, and say you wanted to use the same number of inputs as there are training examples in the original data set, this only costs you $62. So it's very, very feasible to do these attacks, right? And once you've extracted this model, you can then serve it yourself and charge other people to use this, right? So that's kind of crazy from a competitive standpoint. I see a good question here. Do we need to make sure the victim model has the same architecture with the extracted model? No, it's not necessary, actually. So we did some experiments that I'm not going to talk about where these were mismatched. So like this model, victim could be something like XLNet, and the extracted model could be BERT, and it actually works pretty well. In fact, if your victim model is some really, really huge scale model, even if your extracted model is smaller, it seems to work even better than if both the architectures were matched. So yeah, there's some very interesting results here, which are kind of favorable from the attacker's point of view, right? They don't even have to know what the underlying black box model looks like. And so we had this estimated cost for translation, but the paper that I linked on the website actually did this for translation and stole a Google Translate model that had very similar BLEU scores to the actual Google Translate. So, Google Translate is a very, very valuable model, right? And the fact that it can be easily stolen in this way is definitely concerning. So compared to the distillation process that we went over in the beginning of the class, here we're not assuming that we even have access to the original training data of the victim model, right? So if we go all the way back to this example, we were assuming that both the teacher and the student have the same training data, right? And we're just varying the labels that the student model is being trained on. But in this extraction case, we don't even make that assumption, right? This model just observes this random gibberish text, and it's still able to work despite not seeing a real example of a sentiment like positive, negative sentence. And here, like, we don't care about compression. We're simply trying to maximize the performance of our stolen model. So in this paper, we tried it out for sentiment analysis, NLI, which we've seen before, and squad style QA. We used two really stupid input generators. One was the random gibberish sequences that we looked at before. The other one was trying to at least use more grammatical sentences. We just sampled random sentences from Wikipedia. So like even if they had no sentiment in them, we would just randomly sample one and feed it into the model. So for something like squad, there's actually two inputs, right? There's a paragraph as well as a question. So we had like these two settings where in the random setting, the question was a subset of the random words in the paragraph, because we know that there's some kind of a relation between question and paragraph. There was another variant we tried where we added some sort of question-ish words to the random sequence. So we had this random question, Kazim further as, and glowworm. We just added the word what and a question mark at the end. But I mean, these are also very easy heuristics for an attacker to add in if they know that they're trying to steal a QA model. So let's look at some results. Our victim model was getting an F1 on squad of 90.6. So this is like a BERT pre-trained model. The random model was not doing so well if we limited the number of queries to the same number of examples that are in the original squad training set, so like 100,000. But it improves significantly if you multiply the number of random queries by 10 times. So if you use, say, 1,000,000 queries here, you're able to close this gap. We didn't try any more than that, but we assume that as you add more and more, you can close the gap further. The strategy of just sampling a random Wikipedia sentence, and if you do it with 1,000,000 random Wikipedia sentences, you get very, very close to the performance of the victim model without having seen a single legitimate instance of a question passage pair. You can see that on sentiment analysis, the gap is similarly small, and on MNLI, it's a little harder to match the performance of the victim model. All right, doesn't seem like there's any way to prevent this. Yeah, we'll talk about that briefly a little later. But in general, that is true. Yeah, there's not a single method that you can use to prevent these kinds of attacks. Are industry-level pre-trained BERTs readily available? Because if they are, aren't we really only stealing the feed-forward layer? Well, I mean, all of the models that are served by these APIs, right, they have to be state-of-the-art. The way that we know to get state-of-the-art performance right now is through fine-tuning pre-trained language models. So it's easy to assume that all of the models that are being served by state-of-the-art APIs are using this kind of pre-training in some way, right? We already know that Google Search has now switched over to using BERT to do the rankings. So I think this is a pretty fair assumption for most like state-of-the-art APIs. Is it possible that Google Translate is just so good that we are essentially learning from a near human level parallel data instead of stealing the model? Well, it depends on how you're constructing your queries to Google Translate, right? Of course, if you put in like random sequences of words, you will be learning the one-to-one mappings between like different languages at a word level, right? So you'll at least be getting some alignment. If you then just put in like Wikipedia sentences, now you're learning some grammar as well. And yeah, you're just assuming that Google Translate is doing such a good job. Actually, there's an interesting anecdote I heard about this. Apparently, so Google oftentimes mines like parallel data from the web, and they like periodically retrain their models on more and more data that they've collected. And someone was telling me that they noticed, I think this was a couple of years ago, they noticed that some of the text that they were getting was not actually like human written parallel text, but text that other people had passed through Google Translate and then posted on the internet. So they were like training their models on worse versions of Google Translate outputs. So they had to develop some method for like filtering out text that was generated from older versions of Google Translate, which I thought was pretty interesting. But it's kind of not the problem with people attacking or stealing the model, but rather their own previous iterations of the model were making making the current model worse, which is interesting. Does this signify that the underlying model does not matter that much? I mean, of course, you want it to be powerful enough that its predictions are at least somewhat meaningful on queries that have some signal that is kind of related to the task that you care about. But yeah, I mean, the experiments that we've done show that it doesn't really matter if your underlying model is like BERT or XLNet or Roberta Large or whatever. As long as it's producing reasonable predictions, you have a good chance of success from stealing it. Okay, so let's just conclude briefly by talking about some possible defenses, although they are very limited. So there are two that we explored. One is called API watermarking, and the other is membership classification. So we'll briefly talk about both these. The first is watermarking. So here, you, as the person training and hosting the victim model, you understand and acknowledge that there are going to be people who are trying to steal it. And so what you're going to do is from some very small fraction of queries, so maybe like 0.1%, you're going to intentionally return incorrect output. So for example, let's say on this example, Circle Ford had support. The model might predict 29% positive, 70% negative. So instead of returning what the model predicted, I could just flip its prediction, right? And return positive here, even though it predicted negative. So we're going to call this a watermark because we're going to kind of store this in a database that for this particular user, we returned the wrong label on this query that user submitted. And so now, if the attacker is going to fine-tune their model on the data that they get out from the victim model, they're going to include some of this watermark data in their fine-tuning process, right? And we know from things like GPT-3 that these models are incredible at memorizing their training or fine-tuning data. So it's very likely that if an attacker were to fine-tune their model on watermark data, that the model would memorize that for this particular watermarked input, the model would return not the prediction of the victim model, but the opposite of that prediction, or something like that. So if this is happening, because we know that these models are can memorize what they see in their training data, then we have now a method of potentially detecting models that have been extracted from our victim model. So what I want to highlight is if you fine-tune on a watermarked version of the MNLI task, where you have 0.1% of the queries that are watermarked, the model memorizes the wrong label for 87% of the watermarked queries. So now you have a clear way of detecting whether or not a model has been extracted from your victim, right? Because if the model is performing at, if it's predicting the wrong label for the watermark data on a large percentage of those examples, it's very likely that it's memorized stuff from the outputs that you gave it, and so you can maybe try and take some legal action against the whoever extracted this model. Of course, there's a huge limitation with this approach, which is that you're requiring the attacker to make their stolen model publicly available, right? So maybe this makes sense. Oh, I see I'm buffering again. Oh, sad. Okay, let's wait for it to correct. All right, looks like it's working again. Yeah, so I was basically saying that the big limitation of the watermarking approach is that if the attacker doesn't make their model publicly available, like maybe they're using it for some private nefarious purpose, you're going to have no way of knowing if they've stolen your model or not. Because it only makes sense if you're maybe in a setting where you're a company and you believe that another company is serving a model that was extracted from your API, and you can test out whether this is true by measuring that other company's model on your watermark data. But many use cases of stolen models don't fall into this. So this is a very limited approach. There's also strategies that people have proposed since then to even if you're going to make your model public, you can get around this approach if you know that watermarking is a potential defense. Okay, the second approach is also similarly flawed. It's membership classification. So in this case, we are basically saying that we're going to try and detect inputs that seem like they're not really associated with the task. So if I have like a random sequence of words, I might want to have a classifier to predict, oh, this looks like it's a kind of weird input that seems kind of useless for any real customer. So maybe I'm going to return a random label or prediction for this weird example. And as such, an attacker that's using this random strategy is not going to be able to extract a useful model. And so you can train, models to detect whether some attacker is randomly sampling sentences or sampling them from Wikipedia or whatever. But this is really not a feasible defense because you're really limited by the performance of this classifier. There can be many legitimate queries that can be out of distribution for your training data, right? Maybe someone wants to use your sentiment analysis for like legal documents or social media or something that gets flagged by this membership classifier, and your model starts returning random labels. You're going to make the customers mad, right? So really, this is not a feasible defense either. And in general, yeah, so far there is no real defense against these kinds of extraction attacks. Okay, so before we conclude, last question. Is the watermark just the incorrect label or the exact probability distribution? I believe you can do both. I assume it works better with the exact probability distribution, but most of these APIs don't produce the exact probability distribution. So yeah, I mean, it also works if you watermark with just the argmax label, but you likely need a much larger number of watermarked examples to be able to accurately determine if a model has been stolen from your victim model or not. All right, so that's it for today. Sorry again about the internet issues. Hopefully they don't occur on Wednesday. Yeah, and on Wednesday we'll be going over